Okay, so hey friends, welcome to the channel. And today we'll be solving this particular system design problem, which is to design a URL shortener like bit.ly. So in this case, what actually happens is we have, let's say, a big URL like, or similarly like a tiny URL. So for that, we need to design a uh, shortening service. So here we'll spend some time. So bit.ly or TinyURL is a URL shortening service that converts long URL into shorter manageable links. So it also provides analytics for shortened versions. So it will be something. So basically, if I have, let's say, youtube.com/big one, so it will be returned like tinyurl.com and slash something like this. Now this can be pretty big as well, but as of now we are keeping things simple. So what are the functional requirement for us? So users should be able to submit a long URL and receive a shortened version. Users can optionally provide a custom alias or expiration for the shortened URL, and users should be able to access the original URL by using the shortened URL. Okay, so basically we'll give a shortened URL which will hit the server of TinyURL, which will give us the long URL, and using that we'll go to the actual service. So system scale, we have 100 millions daily active users and we need 1 billion shortened URLs. So there are a few things. So basically how we are designing it, we have, let's say, our client. So we have a client here, and what I'm gonna do is I will visit a short URL like this, and short URL, and this is going to be our bit.ly server, which will return to us a status code, which will have our location, long URL, and then we'll go to whatever we were thinking. So here in our case, youtube.com/ which is our long URL, and this is our YouTube server. So like this things gonna happen. So let's just simply discuss about the calculations we have 100 million daily active users, or that means like 100, we can assume kind of 100 millions write operations are going to happen, or like URLs are going to happen. So like URLs a day, and the write operations per second are going to be 100 million. That's a lot, divided by 24, and like 60 in minutes and seconds and all. So this will be around, so this will be like around 1160 write operations per second, and read to write we can assume something like 10 is to 1, which is a pretty common scenario in most of the daily use are in this case. And read operation per second are going to be like 10 times of this, which will be like this. And this storage, so it is given that will be will be having 1 billion shortened URLs. Okay, so first, okay, and the URL length I'm assuming to be, let's say, 100. So the storage requirement is going to be 1 billion into 100 bytes, and this is for a year. So this will be around 10 terabytes per year. And the more our service goes on, and accordingly we'll have. So talking about the non-functional requirements, so these are the statements about the system quality that are important to your users. Should be able to, and this you should. Okay, so talking about the non-functional requirements, what we need is, we need system to be highly scalable. Talking about 1 billion shortened URLs and 100 millions daily active users, we need it to be highly scalable, and we need the system to be available as well. Be highly available again, because we need high availability for a system. What else we need? So availability, scalability. So the CAP theorem is simply consistency, availability, and partition tolerance. So partition tolerance will be always be there, but so we need to make a decision between consistency and availability. So I think consistency we don't need much in this case, because we need, so consistency is basically we have to give the correct data. If we don't have the correct data, we'll return an error. And in this case, we are okay with the stale data, and we'll always show them something. So I think availability is better in this case, unlike the consistency we need in case of banks or payment related things. Okay, availability, scalability, and we need to have a fault tolerance as well. So basically, if we have anything failed, we will have our system running. So system should be resilient or equipped with high tolerance. tolerant. Now, what else do we need for our case? Okay, so other thing is we need to have, of course, the unique URLs, unique URLs that are generated, and we need to have very low latency. So whenever we click, in our case, this tiny URL, we should be redirected to here as soon as possible. So very low latency. So I think this should be enough. Non-functional requirements. Do we have something else? So simply here we have. So let's review our non-functional requirements. Okay, so what we did well is identifying the three key non-functional requirements: uniqueness, high availability, low latency, scalable. And what needs improvement is your high availability. Be more specific. The system should prioritize availability. So like here we discussed like gap theorem. Availability is obviously more important than the consistency. Which operations require? Which operations requires low latency? Redirection latency, right? So here what we need to add is very low latency. In particular, we are talking about redirection. Here I need to have something like this. Consistency and fault tolerant point is somewhat redundant with high availability. Consider specifying what types of faults the system should tolerate and how it relates. Okay. And minor suggestion. Consider quantifying the low latency requirement. While the scalability is correctly quantified, consider adding some time dimensions. For example, handle. Okay, so I think this is a pretty good answer. We'll have again, if everything is consistent, else we'll move forward. Okay, yeah. So I think that is great. So let's move to next question. So here we have to add core entities. So these are fundamental components of your system's data model. They represent the primary objects your API will interact with, and that a system will persist. They can also be thought of as major tables in your database. Core entities are the fundamental components of your system's data model. So we are focused on basically more on the data side. Okay. So in this will, so as here example for core entities will be like user, tweet, follow. So in our case it will be simply we need a user with us first. Second we'll need a long URL, and third we'll be needing a short URL. So consider combining long into a single entity like URL mapping. Okay, so I need to add a other point, which is the URL mapping. Okay, so this is the core function that will be using to map short URL with the long URL. So I think this is it. Okay, great. Let's move to next question. So the API routes that we'll need. So API acts as a contract between your system and its user, guiding your design and ensuring it meets identified requirements. Your API endpoints should satisfy the core functional requirement. So in this case, I think we'll need four API endpoints. I'll have here one, the second, third, and then fourth. So four API endpoints I'll be needing, and we'll be having something as okay. So let's draw it in our case. So here I have user with me like this. I'll have this, and this. So this is my bit.ly, and here I have my YouTube or anything, and I'll send like this here, here, and then back. So in this, what we are doing is we'll be posting one request, which in which we'll be posting our so so in this we'll be having a post request in which we'll be posting our long URL and what it's gonna be like is, so tweet body, and it's going to be, so let's name it something like URL request, in which I'll be having two parameters. We'll have a request, we'll be sending our long URL and we'll be expecting so request parameter and return. So the request parameter, I'll be sending my long URL, and in return I need a short URL, and this is my string. Both are string, right? Both are string. And second is I'll need a redirection. So basically when I have received my short URL, so basically these two only. So these two are the endpoints. So these two endpoints we want, and second so this is the get request that I want, and I want short URL, and it will be something like redirect. And in this redirect will be redirected. So long URL we have sent, we have received a short URL. Now using that short URL, will be going to our main servers. So here we'll simply return the long URL for HTTP redirection. So, so this is the two endpoints, I think. This is the redirection. So this is the redirection, and this is the request. Okay, so let's get feedback over this. Okay, so we have identified two main API endpoints, one for creating, and yep, correct. Clearly shows the flow of requests between the user and URL shortening service. Okay, so we need improvement. Your API does not include support for optional parameters like custom aliases and expiration date, which are key features. Okay, which would make your API more flexible and user friendly. Post long URL needs more. So in this case, we need, what do we need? So aliases and expiration. So more we need is aliases. This is again going to be a string, and aliases and expiration. So this again we can have a string aliases. So minor suggestion is consider using more RESTful naming conventions for endpoints such as post URLs, get URLs instead of, okay, adding HTTP codes to your API documentation would provide more clarity about the expected behavior. So HTTP status code, we have 301 and 302 with us, and 301 redirect. So basically we have a 301 and 302. 301 is permanent redirection. So code 301, which is permanent redirection, and we'll have HTTP code. HTTP code and 302, which will give us temporary redirection. And in this case, here what do we need to return? If we return 301, that means that URL is done. If not, so permanent redirection. So this means that when the client is sending request to our Bitly server, TinyURL server, we'll have two codes, 301 or 302. 301 is permanent redirection. The browser here is going to cache things, and subsequent request will go directly. So let's add. So here browser cache and subsequent requests. Subsequent requests are handled from cache, and temporarily redirection, that means uh, redirection requests will go to our Bitly servers. Redirection request will go to Bitly servers, and I think in this case we'll simply have our HTTP code of 301. So we'll simply cache it with us like this. And more meaningful names. Okay, so it will something like URLs. Slash. So short, I think this is enough. Let's see. Okay, great. So as of now, our API routes are correct. We have identified the non-functional requirements, entities, and our API routes. Let's move on to the next question. How will users shorten a URL? Don't worry about the algorithm for generating new short URLs. We'll get to that later. Great. Okay. So this is our simple architecture of how the URL shortening service will work. So we'll have a client with us here. Let's zoom it a bit. So this is like client server DB, right? So here, let's say we have client with me, and it's gonna send request to our servers, Bitly servers. So here I have Bitly servers, and let's zoom it a bit more. So we have our Bitly servers with us. Then we'll have something core log. So I think in the Bitly servers we'll have all the things, and it is going to query the DB if things exist or not. We'll have our database with us, and simply returning here. So I think this is pretty much it. This is so Bitly servers, and I have simple database. Servers will have the core logic. Uh, so let's write a bit about it. So we'll have the core logic for transforming long URL to short ones. In DB, we'll be saving so in the database, we are going to saving mapping of short URLs to the long URLs. So we can have a cache layer in between as well. So we can have which will be having our database, and so first I think cache, then database. So we can have, and in this case we can use Redis for the key DynamoDB or um, we can simply have a key value store, right? We don't need any fancy stuff. So something like this. So this is our cache, and for DB we can simply have key value based DB. For example, key value based DB, for example, Dynamo I think will work, and simply we can have a cache. We can have some expiration policy uh, to, to serve requests faster. So we'll have our like this, and this is our database tier. Okay, great. Now here we are simply sending request with long URL, and we are getting short URL. So I think this should work. Let's, how will you shorten a URL? Don't worry about the algorithm for generating new short URLs. Will get okay. So the client is going to send the request with a long URL to our Bitly servers, and in that service we'll be defining a core logic or the business logic for transforming our long URL to our short URLs. And then we'll have a database tier with us. We'll have two separate layers for the cache to serve the request faster, and we'll have a database. Mostly we'll be using a key value database because we have one-on-one mapping of short URLs to the long URLs. We'll be using that database tier to store the short URLs and long URLs because short URLs are unique, and and saving in the database, we can prevent collisions and all. And then we are going to simply return the short URL back to our client. So let's get our feedback. Okay, so data schema. So data schema, key value based thing I have given. So what else we can have? So schema, so key is going to be our short URL, and value is going to be the long URL. And what else? What else we can have here? Expiration time. So long URL, we can have multiple things. So next we can have an expiration time. We can have a creation time, when it was created and created by whom, and our client ID or user ID, something like this. But I think so. I think this should work. Let's see. Great. Okay, so we have done. Okay. Consider elaborating on how users might interact with the system through web interface, APIs, etc. So here the client, how the client is gonna interact. So we can add some details over here. So something, so through web browser. So web browsers we can have some kind of apps with us, and I think that's pretty much it. Web interface, API. So we can have a program written with us that would let's say some kind of Excel and all. So for that we can have an API exposed. User ID, I have client ID and created by. Hmm. Okay, so these are like minor suggestions. We can add over here client ID we already have. We didn't get it, I guess. And we have created by we all have user ID. This already have. Okay, let's move on to the next question. Okay, so now we need to have a redirection thing. So how will users be redirected? Okay. So we have not completed this. Yep. How will users be redirected from a short URL to the long URL? So when the client is sending a short URL to us, huh, so let's draw it over here. So this is our client and we have web browsers, API, apps, etc. So here, hmm, so we have our Bitly web servers. So we have our Bitly servers with us. In this case, these servers, what are servers doing? Servers are receiving. So, so we have our, where is, so these are the two endpoints, right? So this is done and this get we have to do. So here we are simply doing this thing and the servers are going to query our DB to get the long URL. Yep. So we have this one. This is our database tier. We have two components to it, cache and a DB, which are communicating. other. We'll have our cache and our database, and this is sending the long URL return long URL. And in the servers, what we are doing is we are simply querying our queries our database to get the long URL based on the short URL provided, given it is not expired. So I think this is pretty much it. Let's submit our answer. So how the users will be redirected from a short URL to the long URL. The client is going to click on the short URL, which and it will be redirected to our Bitly servers, which are going to query the database. As we have a key value stores, we'll have a long URL associated with a unique short URL. Given the short URL is not expired, we are going to simply return the long URL. If it is expired, we are going to send the error code or the URL expired kind of notification to our users. And in a database tier, we'll have cache and database both. So we can have different cache expiration policy with us. Okay, so we have everything covered. Minor suggestion: consider explicitly including HTTP mechanism in your design using 3. Yeah, so for that, redirection is HTTP 301 as we had discussed previously. So which is HTTP redirect 301. So we have a client which will click on the short URL, which will then the request is going to be sent to our Bitly servers. Servers are going to query our databases to get the long URL based on the unique short URL which we have. And if the long URL is not expired, we are simply going to return that. If it is expired, we are going to return some kind of error message. We'll have a HTTP redirect of 301 so that we can cache so that we can have it cached on the client side browser and all. In the database tier, we'll have a cache and database to have low latency, and database will be a key value store. So 302 redirects offer better analytics tracking capabilities. Okay, so let's write it down for notes. So 301 better for browsers caching. Better for browsers due to caching, and in this case better for analytics tracking. Okay, let's move on to the next question. So how can we ensure that each shortened URL is short and unique? So in this case, what we have to do is, let's move our DB here and let's zoom on to this particular thing. So let's keep it aside a bit. So in this case, we have, I think, something called as the base 62 conversion. So we have a base 62 conversion, and so basically we can have 16 unique characters. So the mapping is something like 0 to 9, which are numbers, then A to Z small, and then capital A to Z. So here we have a long URL with us. Now what we gonna do is, long URL will generate a ID. and this ID we can have a base 62 conversion. And we'll simply get the short URL. Now how this unique ID generate. So this will be like a unique ID generator with us, with everything numeric. So I think for this we have something called as snowflake approach or something which create a numeric which creates a unique ID. So here we can use Twitter snowflake approach to create a numeric numeric what? Numeric unique ID. So I think this should work. Let's see what happens. Okay, so the client sent the request with the long URL to us. Then using that long URL, we are going to generate a unique numeric ID for that particular long URL using like Twitter snowflake approach. We'll be using that specific time, machine ID, data center, like that. And using that ID, we'll do a base 62 conversion on that ID. And then we'll get our simple short URL, which can be alpha, which can be numeric, and which will be alphanumeric, and will send that short URL back to our client. Okay, so minor suggestions that we have is explaining the Twitter snowflake approach. Yeah, so machine ID, sequence number that had said. It would be helpful to address how your solution ensure that short URLs will remain under a specific character length. You might want to elaborate on how your system would handle the unlikely event of collisions, especially in a so collisions will happen. I don't know Twitter snowflake approach take care of everything, but what we can have is to explain the Twitter snowflake approach. So, we'll have our Twitter snowflake approach. So basically what we have is, in our case, it will be something like how many bytes, how many bits, 64 bits long, and we'll have divided it into multiple things. So this is like the signed thing. We'll have our time here, we'll have the machine ID, we'll have the data center ID, and we'll have the sequence number or something like that. So this is how the uh, it is going to be, and we can have like number of bits divided accordingly. So it is like 5 bit, 5 bit, 12 bit, and how much is remaining? 22, 23. We have like 41 bits here. So this is how the Twitter Snowflake approach works. Let's write it down. So generating 64 bits, ID 1 bit is going to have a signed unsigned differentiating factor. 41 bits are for the timestamp, 5 bits for the machine ID, 5 bits for the data center ID, and 12 bit for, so basically on that machine in a particular center we'll have a sequence. So for that we have a sequence number or ID with us, and if we have 64 bit 64-bit integer with us, and so max length is 11 characters, and collision given our requirements will not happen. Okay, let's submit this again. So the client is going to send the request with the long URL. Our servers will receive the long URL. We are going to generate a unique ID based on Twitter Snowflake approach to create a unique numeric ID. And talking about Twitter Snowflake approach, we'll be generating 64 bits ID, which will be divided into a few things. One bit will be giving it for signed and signed thing. 41 bits will be using for timestamp so that we have a unique ID with us. 5 bits for the machine ID, 5 bits for data center ID, and 12 bits for the sequence number on that particular machine. Now, if the maximum characters of the tiny URL or the short URL that we'll have is going to be maximum of 11 characters, because we'll be using a base 62 conversion on the ID received from the Twitter Snowflake approach. And talking about the collision, that would rarely happen because of the requirements that we have. And once we get the unique ID, we'll have a base 62 conversion on that, and we'll simply get the short URL with us. We can have a database in which we'll save everything and we'll simply return the short URL to our user. Okay, great. So everything is going fine. Let's move on to the next question. Now we have to ensure that the redirects are, are fast. Now coming back here, so I think we need to spend some time on the cache. We can have some. So mostly I think this should work. So in this case, we'll be using a cache. So we'll be having, for example, Redis with us will store uh, Redis because it store everything in memory. We can serve it faster. Key value based database with us. What else we can have? And we'll implement least recently used, some kind of expiration policy in our cache to serve the request fast to serve the request fast and avoid redundant data. So in this we can have least frequent. We can have least recently used policy for least free LFU. I think would be better. Frequently used policy for our cache. And we'll be using HTTP redirect 301. What else? We can have a rate limiter, maybe. So this is our rate limiter to limit the number of requests sent to server and prevent denial of service DOS attack. So this is the rate limiter use case. What else we can have? How can we ensure that redirects are fast? So caching is done. So I think this should be enough. Let's talk. So the client have the short ID and it clicks on it. So we don't want to overwhelm our servers with excess number of requests, and we don't want to have a DOS attack, denial of service attack on our servers. So we'll have a rate limiter in place. Then the request is sent to our servers. If it is in the rate limiter algorithm, then our servers are going to query our cache first, and if the long URL is there in the cache, we are simply going to return to our client with the HTTP redirect 301. We are using 301 so that we can cache it in the client's web browser easily. Second, for our database, if the long URL we don't find it in our cache, we are going to query our database. We'll be using simple key value based database like DynamoDB. So because we have a short URL which is unique, which will serve as a key and will query our database quicker. Now we have saved our data to our database. We'll save it in the cache as well. We'll have some kind of expiration policy for our cache so that we can serve the request fast and we can avoid the redundant data. In this case, I think least frequently used policy would be the best for our cache, because if some particular URL is not being used frequently, we can simply evict it out of our cache. So this is how I think the request flow is going to look. So let's see what will be the feedback. Okay, lovely. Okay, so we have a few things that we can have is elaborating least frequently used, include details about expected cache hit ratio and strategies to optimize it based on traffic patterns and URL popularity distribution. Discuss cache sizing consideration based on expected traffic volume, memory constraints, and the trade-off between cache size and hit ratio. Okay, so I don't know about cache sizing, hit ratio, things like that. Study. I need cache hit ratio and strategies and sizing. This is going expected of traffic volume, memory constraints, and trade-off between cache size and hit ratio. Okay, let's move on to the next question. How can a system scale to support 10K redirects per second? So as of now, isn't it supporting that already? Hmm. So scaling a system, we need to support read requests. We're not writing anything, so we can simply have a master follower replication. Easy. So what we'll be doing is we'll be having this as a master, and we'll be having multiple replicas of this database. Like this, and these are going to be eventually consistent. Consistent, and we have master database, and we have follower databases with us. This is going to handle the write request, and these are going to handle the read requests. Easy. So let's check. So to scale our system to support 10,000 redirects per second, and we are talking about reads specifically, we can follow master follower kind of database tier for our use case. We'll have our master database in which we'll be redirecting all our write requests, and we'll be having follower databases in which we are going to redirect all our read requests from our servers. And the follower databases and master database are going to be replicated, and will be having eventually consistent model because we want high availability for our system. Now, if we have, let's say, 4 is to 1 or maybe 10 is to 1 reads to write ratio, we can have more follower databases so that they can handle more read requests in parallel. So this is how we are going to scale a system for read requests. Okay, great. So cache hit ratio expectation, I don't know. Explain how the system would efficiently handle cache misses to maintain performance. Okay. How would you maintain consistency between master and follower databases? Eventually, consistent model. Uh, what is eventual consistency? Cache misses to maintain performance during peak load. So, what are cache misses? So, cache misses. Query db. This I don't know. Let's try again. So to scale our system to support 10K redirects, specifically read per second, we can have a master follower database tier with us. In this, we'll be having a master database, which is going to handle all the write requests, and we'll be having several follower databases which are going to handle the read requests. And we'll be having eventual consistency between master and the follower databases, which means that the follower databases are going to be asynchronously the follower databases are going to take data from master databases asynchronously. And in the case of cache misses, we are going to simply query our database directly at the time of peak traffic. So yeah, I think that's pretty much it. Okay, so I think this is how our whole design or URL shortener is going to look like. Um, So we have, let's just recap everything what we have seen. So the functional requirements are user is able to submit a long URL and receive a shortened version. We can have custom alias, expiration date, etc. for our shortened URL, and user should be able to access the original URL by using the shortened URL. And the system scale we have is 1 billion shortened URLs and 100 million daily active users. So the non-functional requirements that we got is it should be highly scalable, highly available. It should be fault tolerant. We need unique short URLs that are generated, and we need a very low latency during the time of redirection. The core entities that we need is the user, the long URL that is needed to be shortened, and we also need a URL mapping. So kind of mapping between short URLs and the long URLs. The API routes that we have is basically we need two main endpoints. One is the post URL. So these are the REST API URLs. REST API requests. We are going to request the parameters, which are long URL, aliases, expiration, all in string, and what we'll get in return is the short URL. And for the redirection, we'll be sending the short URL, and from that we'll get the long URL. So for that, we have two separate HTTP code with us, 301 and 302, which will be sent from our Bitly servers with the short URL. 301 is the permanent redirection, which is the browser will cache the long URL and the associated short URL, and the subsequent requests are handled from there. And we have HTTP code 302, which is temporary redirection. That is, every redirection request will go to our Bitly servers, but it is very useful for analytics. So if analytics is priority, we'll be using our HTTP code of 302. And talking about the high level design, in this, the core logic of transforming long URL to short URL, the client is sending the request with the long URL. We are going to generate a unique ID based on Twitter Snowflake approach. Then we'll have a base62 conversion on that unique ID. The maximum length can go to 11 characters. Then we'll simply get the short URL in our database. We are going to save it, basically a key value store, and we are going to simply then return it to our client. And for the redirection, we'll simply have a rate limiter in between just to limit the number of requests sent to us. We'll have servers which are going to query our database, and we'll have a cache with us to serve the request better. We'll have the database in which we'll be having key value mapped for all the short URLs that are generated. And to scale a system horizontally, we can have something called as master follower database tier, in which master is going to handle the write request and the followers are going to handle the read requests. So that's, I think, pretty much it about the short URL shortener. So that was today's video. See you in the next one. So let's submit this. Complete practice. Yep, done. Okay, we can solve some lead code as well.